Welcome back. My name is Maru Walliser. I am co-chair for the Lectures Committee for the Princeton Adult School, and I have a few announcements first. If there was anyone who didn't get the schedule for the rest of the term, there is a lovely gold-colored sheet because there will be 3 lectures over at the Carl Field Center on campus rather than here, so be sure you have that sheet. The other thing is I've been asked to tell you that the library here at John Witherspoon is looking for books in foreign languages for middle school children. Now that's a bit of a special order, but if any of you have such things and you could bring them here on a Tuesday evening, we would give them to the library, okay? Any language, but I am told they speak 50 different languages here in the school. So you name it, you can bring it, okay? It's my pleasure this evening, really, to introduce our lecturer, because in 2012, when the Institute for Advanced Studies announced that its new director was Robert Dijkgraaf, then the president of the Royal Netherlands Academy of Arts and Sciences and co-chair of the Inter-Academy Council, the story was featured on the Dutch Evening News and was cause for much jubilation among scientists and non-scientists alike, both sides of the Atlantic. Why? Because the new director is a modern Renaissance man of sorts, or as one of his colleagues at the Institute said to me, he's an intellectual rock star. He's a painter, a mathematical physicist. He writes a monthly column in a leading Dutch newspaper and makes frequent appearances on Dutch television, where he explains esoteric theories of quantum physics and string theory to general audiences like us. I happen to know he can do this because I heard him speak a little over a year ago, and I was quite sure, to my own amazement, that I understood what he said about the universe. I've been on a mission ever since then to share that experience with you and to have him speak here for the adult school. Professor Dijkgraaf's research focuses on the interface of mathematics and particle physics, and he continues to work on string theory. He'll tell you about that. String theory, he says, and I quote, is the most promising theory that unifies all particles and forces in nature, including gravity. It answers fundamental questions about the symmetries of nature, the quantum behavior of black holes, the existence and breaking of supersymmetry, and the quantum treatment of singularities, unquote. If that puzzles you, as it does me, the good news is that he is a major force in bringing scientific information to the general public and on advancing science education. He works at the nexus of science and society, has written several books for general audiences, as well as the news column and the appearances on television that I noted earlier. He's a passionate advocate for both science and the arts, and he has developed a website for children called Proefjes. Did I say that? Which I think translates as little experiments. I'd like to think of them as proofs for fun. If you can't read Dutch, it's okay. It's worth looking at that website for its charming art and its color. After earning a bachelor's degree in physics at the University of Utrecht in 1982, Professor Dijkgraaf took 2 years to study painting. If you look at the Christmas cards from the Institute for the last 2 years, they feature his work. He returned to Utrecht to earn his PhD with Nobel laureate Gerard de Hooft in 1989. And he was a research associate here at the university from 1889, oh no, not that. 1989 to 91. Then at the Institute as a member and visitor in 1991 and 2, and again in 2002. He knows the neighborhood. For his contributions to science, in 2003, he was awarded the Spinoza Prize, the Netherlands' highest scientific honor. The list of many prestigious academic societies to which he belongs as a fellow or a member, reads like a litany of international intellectual institutions. Before his return to Princeton in 2012, he had accumulated a large array of honors and prizes for his scientific work, and you can read those on his website. But mostly, he now has a prize named after him in the Netherlands that's given annually. Professor Dijkgraaf continues to hold a prestigious professorship at the University of Amsterdam, and he frequently travels there, among a lot of other places in the universe. Given his busy schedule, we're really fortunate to have him here this evening. So please join me in giving him a very warm welcome, Professor Robert.
Thank you so much. That was actually the nicest introduction I've ever had. So, so thank you. That's actually terrific. Great honor to be here, if only to stand in the auditorium that my daughter, who's actually a student at the middle school, is often at. Usually she's on the podium singing or dancing or playing music. Very happy to be here and actually to speak to you and to be as an absolutely lovely the last 2 years for me and my family to be kind of back in Princeton, and which is, I think, really one of the most marvelous places in the world, certainly if you are a scientist and you enjoy the great kind of intellectual treasures that are here. Actually, I want to speak about a lot tonight. Actually, perhaps you know these famous words which I think were once said of Churchill: I wish I knew so much about something as he knows about everything. Might be right for you, because actually I feel that, you know, with my present position at the Institute and experience, it would be perhaps fun to kind of take a bird's eye view of knowledge. How does science work? What are the pluses and minuses? And I want to kind of start by what I always find a beautiful metaphor, that science is about kind of looking on the other side of the hill. That's actually a quote from the Iron Duke, Arthur Wellesley, the Duke of Wellington, who said that both in war and in business, you try to figure out what's on the other side of the hill. He took this quite literally. He would take, when he was retired, with his friends in a stagecoach, go over the hills, look in the landscape, and then they would argue, you know, what would be the landscape behind the next hill? Would it be a lake? Would it be a forest? And he was very good in that game. And so I think actually that's what we often do in science. We really try to predict the future. We're trying to see what's there, and we need some kind of a tunnel vision. Often I see this with young people, that they see things that other people don't see. Take up little hints and explore these unknown things. So I think this is a beautiful example of this process. It's a heroic image of Herschel, the astronomer. By the way, he was a composer before that. Discovering something amazing. So here is an experiment where he actually measures the temperature of the rainbow. He first measures in the blue light, then in the yellow, then in the red, and the red turns out to be hotter than the blue. And then he does something remarkable. Here is just measuring the temperature of something you can't see. And it's even hotter. So this is the glorious representation of the discovery of an invisible thing, namely infrared radiation. And so I think that's a great metaphor, that you look at the rainbow, you know, actually that rainbow doesn't stop at the red or the violet. It goes all the way, from radio waves to ultraviolet, to Röntgen and X-ray. And in fact, a modern astronomer will look at the world, not just like we do with our eyes, but looks at the world in all these different kind of radiations, and see different pictures. So I think that actually is a wonderful metaphor what science is doing. It's opening our eyes to things that we didn't see. And for instance, now you can look at the sky in microwave radiation. This is a famous picture. This is a picture you have seen undoubtedly many times. From basically, often it's described as the baby photos of the universe. That's something that you see if you look at the radiation coming essentially from the Big Bang, 400,000 years after the Big Bang. And a fact that was actually discovered next year, it will be exactly 50 years ago, very close here to Princeton. That's actually with in the bell of orders, V8. And it's these small fluctuations that you see here which actually are telling us an incredible amount of the universe. And I'm showing this because the amazing thing I think we learned about the universe the last decade is, as I like to say, we know exactly what we don't know. In some sense, we discovered that 95% of the universe is missing. That is to say, using Einstein's equations, you can indirectly, in terms of the properties and the curvature of the universe, see how much energy is there. And then you can see how much of that energy do you recognize in terms of matter and radiation and big clouds of gas. And all of that adds up to 5%. And then we know that it's roughly 27% is some form of matter, and which we call dark matter, and the remaining things are a new form of energy, first conjectured by Einstein, that we call dark energy. But dark matter and dark energy are just fancy words for labeling our ignorance. So often I ask people, what is your percentage of dark matter? In your own discipline, in your field, how much do you know that you don't know? For instance, if you study Greek literature, ancient Greek literature, roughly 5% of the works have been survived. So you're literally in a similar situation. I think actually 95% dark matter isn't such a bad number. I think that's my general take on this. And so often I feel this. This is roughly what we're doing. In the good cases where we know but we don't know. We're like the medieval map makers who had great difficulty leaving empty blank spots on the map. They fill them in with these marvelous sea monsters. And often I feel, well, the scientists, they're up there, in this little boat here, floating in between the sea of the sea monsters and chasing them away. And, you chase them away by just kind of mapping out the universe. And so I want to talk to you about the present day sea monsters and how are we dealing with them. And as I said, kind of the known unknowns, which became famous. There's the third category, the unknown unknowns, became famous, of course, in this very, very relevant situation of the invasion of Iraq. But actually, the 95% missing in the universe is an example which, like 10 or 15 years ago, wouldn't even be mentioned. So we weren't even aware that we didn't know them. So at that point, it was an unknown unknown. Now it's a known unknown. So which is great progress. And I think it's important to stress that that's the very nature of science. You always make this kind of discovery. I like this quote of science as organized skepticism. And this is a quote from Francis Crick, who said that the theory that accounts for all the facts is wrong because always some of the facts are wrong. So if you read and hear about us scientists going for a theory of everything, a universal explanation, it's always in this, we try to approach this, but we're always aware that nature could actually play some tricks upon us. And I just want to share one example, I think actually a wonderful example, perhaps you've read it before. It was a big debate in England because somebody was making an omelette and breaking an egg. And it turned out to be an egg with 2 yolks. And then she broke the second one, 2 yolks. The third one, 2 yolks. At that point, hubby was in the kitchen, pictures were made. 4th egg, the 5th egg, 6 eggs, all of them double yolks. How could this happen? Now, roughly 1 in 1,000 eggs has 2 yolks. So to have this 6 times in a row is absolutely marvelous. And then there was a wonderful debate in the British press with all kind of chicken and egg experts commenting on this. And I really liked that debate because it was like, these eggs were selected in size, perhaps they were coming from one chicken, there were hormones involved, we should check the DNA, etc., etc. And then one of the experts mentioned that he was walking in the supermarket. At some point he saw boxes labeled double yolk eggs. So I think this is just very refreshing. So I think we'll always be aware that this we might have this equivalent of the boxes of double yolk eggs here. I also want to speak of imagining the future. I'm just talking that the Prince School is 75 years old. And actually doing some research, on April 30th this year, it will be exactly 75 years ago that in New York, the World's Fair opened. And the theme was the world of tomorrow. It's actually quite interesting, you know, that was the first time television was presented, actually as a kind of a Skype, you could actually even, there was electric kitchens, etc. But what I read actually, the opening lecture was given, well, President Roosevelt spoke, but also Albert Einstein, the most famous faculty member of the Institute. The first, I always say the Institute, if your first professor is Albert Einstein, it's downhill from there. So we have 80 plus years of decline. And he actually spoke on the subject of cosmic rays. And the opening act was he would capture 10 of these cosmic rays, and then by a vacuum tube, actually in the Hayden Planetarium, they would be sent by telephone to the World Fair, which was in Queens, and then a big switch was, and then the whole thing would light up. Well, first of all, the amplification system didn't work, so people only could understand the first 5 words of Einstein's speech. And then when he finally switched the electricity on, there was a big power failure and the whole thing collapsed. And people left, and then the New York Times reported that people deserted science to see something they could applaud. So it was a total failure. But it's interesting that, you know, at that World Fair, there were many things that you could see in the future, but some things were not there. And particularly I want to highlight 2 points, nuclear physics and computers. And I'll highlight them because actually you could actually go down to the Institute and actually would meet both of them. Or at least the first. Of course, Einstein, even though he gave the opening speech, it would only be that summer that he would write a famous letter to Roosevelt starting the atomic bomb project. And at that time, I think he himself even made the remarks around that time that there was no practical use of atomic energy at that time. So it's interesting is that the Institute was founded in the early 1930s with an explicit aim to provide kind of a haven for research. Also a haven for researchers, of course, that at that time were, in many scholars were at risk in Europe. And the founding director, Abraham Flaxman, had this wonderful notion of the useful knowledge, the usefulness of useless knowledge. He was very upset that at that time there was a very practical streak in research, in higher education and in research in the United States. And he wanted to provide this environment where people could really pursue their dreams and their deep thoughts. And it was very wonderful that Einstein could come there, but of course he wasn't invited there because he could play a role in terms of nuclear energy. And when the first mathematicians were invited, it included John von Neumann and later Kurt Gödel, who were really attracted because they were stellar mathematicians. They were very interested in mathematical logic. They were interested in mathematical logic and how you could make formal computing machines. And that line of research, Princeton was the center of mathematical logic in the 1930s, and that led actually to von Neumann, 10 years later, building the first modern computer. That is a computer which was not of the type where you build a new machine for every new task. So almost like for every new app you have to get a new phone. Von Neumann knew that now you could program a computer. There's a way in which you can make a unit. This is actually an idea that goes back to Alan Turing, which was invited by von Neumann to Princeton in the 1930s. So the Institute became the beginning of, played a very important role in the beginning of computing. And the amazing thing, this is the floor plan of the Institute in the 1940s. You would see Einstein, von Neumann, and Oppenheimer all in the same corridor. Einstein at that time, the father of the peace movement. Of course, Oppenheimer, the third director of the Institute, very much involved with the atomic bomb, but also having kind of mixed feelings, you know, being caught in this, the Cold War issues. And von Neumann, who's often is being described as the coldest of cold warriors, who was absolutely convinced that the nuclear arms should only be developed, but should be kind of used. And they were all three on the same corridor in a place that was to be totally isolated from society, you know, and have no practical result at all. I think that's a very powerful metaphor. You couldn't even think of this. If a novelist would come up with that, you would say that's totally unrealistic. In fact, the original machine was very small. It had a memory of 32 by 32. Just amazing. Less than 1,000 bytes. And what I always liked is that in the spare time, actually von Neumann did weather complications. So this is a picture of the first computerized weather prediction done in 1949. And I like the fact that it took 48 hours to predict tomorrow's weather. So not even the world of tomorrow, the world of yesterday, it wasn't predicted. But then von Neumann got it down to 8 hours, and then he makes a remark that this actually will be extremely important for the future. And what I find very touching, that in 1955, at the high point of the Cold War, he's asked by Fortune magazine to write an article that's actually available online under the title, Can We Survive Technology? And only a small part of it is about nuclear arms. In fact, most of it is, we would say now, about climate change. About the fact that we inadvertently and also we could actively influence climate and could have a much bigger impact. And as he says himself, it would kind of entangle the interests of countries much more than war would be. And then just a little anecdote, and just, it's not so easy to actually make a hurricane. Of course, last year with Sandy, and somebody came up to me and said, well, this was, as you know, had some impact in the presidential election. So somebody came up to me and said, well, we'll see how many other conveniently timed hurricanes we'll have in the future. So we're not yet there, I think, But von Neumann then actually goes on to describe these great challenges. And I think in the end, he is positive. Although he doesn't give a way out how we can survive, he makes this beautiful remark that the problems can only be solved using our human qualities: patience, flexibility, and intelligence, which I think are pretty wise words. And I think actually, in terms of prediction of the future, this prediction that climate change will be important, done in 1955, I think is quite telling. In fact, there is a book which I think very much in the same spirit by Martin Rees, famous astronomer, often frequent visitor here to Princeton, written Our Final Century. He actually addresses the same issue about the way where we can survive the 21st century. And I think it's important to realize that technology and science has these dual sides. Certainly, I think these days often it's all presented in a very optimistic way, but going back, and I'm personally very touched by, if you go back to the 1950s, you would walk in the corridors of the Institute, you would very much, I think, be aware of what's often called the lights and shadows of science. I want to talk a little bit more about this useless research. It's actually good to take a longer point of view. If you look at electricity, that was actually quite a kind of esoteric phenomena in the 19th century. And there's a famous description when the first electric light is switched on, which actually is in the editorial room of the New York Times. It's switched on by Edison himself. And so you think with a big headline, beginning of the electric age. It's actually, I think, on page 8, a little thing. It says, well, these electric lights, they're like gas lights, but they don't smell. So it's very difficult to see, where technology and science is bringing us. Take quantum mechanics. Quantum mechanics started in a kind of a very dramatic period of physics. Planck himself said it was an act of desperation. So more than 100 years ago. And of course, there was a small group of very bright physicists discussing this. The structure of an atom, elementary particles, would be very far removed from reality. I think it's honest to say that these days, at least 50% of all our industry is based on quantum mechanics. Anything that involves a laser, a computer, any kind of form of electricity, these days use the laws of quantum mechanics. And take another bizarre phenomena. Almost 100 years ago, superconductivity was discovered. It's the phenomena that if you make materials very, very cold, they can conduct electricity without any resistance. What were the consequences of this? Well, there are many. It's now used, of course, in transportation, magnetic levitation. It's used whenever we need a very, very strong magnet. So, for instance, any fMRI scan uses these superconducting rings. In fact, you could say the whole field of brain science has been opened through this discovery. In fact, the coldest place in the universe, as far as we know, is over here in CERN, Geneva. It's actually the magnetic ring, the magnets that built this atom, this elementary particle collider, a large hadron collider in Geneva, is, we think it's the coldest place in the universe. It's cooled down to a temperature much lower than the temperature of empty space in the universe. And it can only be done through the same effect. So, in fact, a fundamental effect in physics, through all kind of science and technology, leads again to very fundamental physics, namely our discovery of more particles. And I think you all witnessed this wonderful discovery, which was the 4th of July, 2012. Actually, it was my third day in my new job. The discovery of the Higgs particle. As you know, it's now called Higgs Dependence Day, which was a tremendous success, and only possible through these technologies. And in fact, this December, Higgs and his colleague Englert were awarded the physics prize, and it's good to, Nobel Prize in Physics. It's good to realize that they got this prize in 2013 for a papers they wrote in 1964. In fact, the first time Higgs talked about this paper was actually at the Institute. Freeman Dyson, our very cherished professor, invited him over. And Higgs has described that he was driving over to Princeton and was, just a young man. And he was so nervous that he was shaking and he had to kind of stop the car on the motorway just to calm down, because he would talk about it. But what I found fascinating, that some of the other architects of the modern world of particle physics were sitting behind on the screen. They were over here. Frank Wilczek and David Gross, both, Wilczek was a professor at the Institute Gross at the university, and my thesis advisor, Geert de Hooft, and his thesis advisor, Martine Veldman, was sitting there. They all wrote papers later than Higgs and got their prize earlier. And then you see, if you're a scientist, if you're a physicist, you can make a prediction like Higgs, which is a 50-year prediction, almost 50 years from the first paper to the effect. And some are luckier, they make a prediction which is 30 years. But some people make predictions which are 100 years or perhaps 1,000 years. So at that time you won't actually earn any Nobel Prizes to be... But we should be aware of this long-term thinking in science. And so the fact that we have these wonderful structures in elementary particle physics is absolutely amazing. If you just see the outcomes of these particle colliders, you see this, I think this is technically described as just garbage. Is there any structure hidden in that? And it's absolutely fascinating to see, if you go through the course of history, there have been really ups and downs as to the question whether there's an answer. Is nature organized in a systematic way at the smallest levels? And in fact, in the 1960s, there was this kind of feeling that no, it's like a black box that you could never open. You have something coming in, something coming out. It's consistent, but you have to have a kind of holistic approach. It's what was called the so-called S-matrix theory. I always found it interesting that in this kind of period of the hippies, it was founded, based basically in Berkeley, California at that time. And this couldn't be more wrong. Because actually what turned out that in the 1970s, using this metaphor, the box could be opened, and inside was a very tiny formula. So here I used the full power of mathematics to write an equation that actually captures all of the physics that we can see around us. All the elementary particles. I just write this equation because I can give a lecture to a mathematician about this equation. And he or she will recognize all the symbols and will agree they're beautiful and natural and elegant. And what I wonder that this describes the world around us. Of course, this is not the way you get the equation taught in a physics course, and you get it more like this. This is actually from a course of my thesis advisor, who really likes to show all the details. Impress students, scare them away, I would say. But another way to put it, you could actually put it on the t-shirt. Now, it's with the discovery of the Higgs particle, there are now 17 particles that capture everything around. And actually, most of these particles you won't actually need to build the matter that are around us. Some of them are very exotically, live for very long, short periods. And I think that's absolutely amazing. That in some sense you can cook down, you can build this whole world around us. To be honest, the 5% that we, I think, understand in terms of these particles. So, particle physicists have two feelings, two minds. So one is an absolutely victory of science. What a beautiful structure. And then there's a second way to look at it. As one physicist famously said, who ordered this? Why these particles? Why these properties? Where did it come from? What is the structure behind this? Can you explain? And as always in science, any answer will generate more questions. And so we look at these structures and we try to rearrange them. For instance, these particles can be rearranged in other ways, which suggest a bigger symmetry, deeper symmetry. So we talk about grand unified theories, where even the different forces and particles come together in a more meaningful way. For instance, once we observed that the four fundamental forces that describe the Standard Model are very different. But if we tune up the energy, if we go to higher and higher energies, or smaller and smaller scales, then they start to change. And in some sense, at some point, they seem to be all roughly at the same strength. So every hint of nature takes tremendous effort. Like the accelerator that's built in CERN was like 30 years of planning, building, 10,000 people. The experiments are done with 3,000 people per detector. And just to get another hint of nature. And we look at these hints and we say, what is she trying to tell us? And I think there's a kind of an aspect of human nature that you want to unify everything, And so we feel that there's something beyond that. And as I said, there are many reasons. There's certainly also a reason that just the cosmos is telling us. That, as I told you, there's so much more matter than the matter that we observe. Astrophysicists, cosmologists tell us that an ordinary galaxy is actually surrounded with these enormous clouds of dark matter, which contains 8 times more matter than the visible matter, and are in some sense absolutely essential for the structure of the universe. So often I like to say we are like the lights in the Christmas tree, but the Christmas tree, we have no idea what it is. It's pitch dark. So it's all out there. And so I think that's absolutely fascinating. And often people ask why do you have such a fascination with the elementary building blocks? And sometimes it's debated, if you would have to pick one thing in all of science, I would say it's the most important thing that's out there, what would you pick? Actually, famous physicist Richard Feynman, picked the following thing, and I think I agree with him. He said actually, the fact that matter consists of particles. If you know that, it totally changes your view on life. For one thing, this is my favorite metaphor, suppose these are 2 toys, the 2 cars. One is made of metal, the other is from Lego. Suppose you give them both to a child. And then look back what happened to the 2 toys, say, a year later. Well, the car will still be there, the left one. I'm sure the right-hand side, something else will be made. The moment you know that matter consists of particles, you can start to rearrange them. It's not only finding the structure, it actually means that you can actually start to build things. So in fact, this is, I think, right a transition we're going into. Of course, chemistry was first there. We're not only the place that observes the universe, but knowledge of the universe actually also means that we can kind of intervene. We can kind of start to rearrange the universe. And I think we're really now in a time where with nanotechnology, in principle, we can arrange each individual atom in any pattern we want. That is to say that the kind of materials and that we have been studying up to now in physics, which are the naturally occurring ones, are only just the beginning. We can try to build any matter we want, and then study it, and study its properties and find its laws. In fact, it's much more. We cannot only intervene in matter, we can intervene in ourselves. We're living in a time where actually we are doing the same thing with life. We are in the time of what's called synthetic biology, where we are creating life, of elements of life, of legal blocks of life, and this means that instead of an old biologist who would just look at all the organisms, animals and plants that have been emerging in 4 billion years of evolution, we can say, well, it's only the beginning, because now we take over. So we make things ourselves. So if you think about the phenomena, the natural phenomena, the things that we have been studying for this moment, is a totally infinitesimal fraction of the total space of possibilities. Think of all the possible organisms that you could make just by kind of writing DNA sequences. Think of all the materials that you could compose. So I think we often feel that, you know, we scientists are almost becoming designers now, because we have to think of ways how to explore this infinite space of possibilities. Where do you find the interesting questions? I think this is really a moment where we are in a transitional period. Also related to this is the growth of knowledge, which is quite spectacular. So this is the seal of the Institute. The first thing when the Institute was started, the founding director said, I need a seal. So you had an artist, it's beautiful, you know, you ask an artist to represent the core value of what you're doing. Truth and beauty. And it's always the question is, which of the two ladies is truth and which is beauty? And then I have to say, truth is naked, as you understand. And often I have to explain those beautiful t-shirts and sweatshirts you can buy at the Institute. Then I also have to explain my children, you know, why is your father walking with a naked lady? But I actually want to point out a third element of the seal, which is actually the tree behind the two muses, which is the tree of knowledge. And the tree of knowledge has grown rather rapidly. This is the tree of knowledge in a manuscript at the 13th century, where the number of disciplines was just a handful. If you go to the 18th century, the Encyclopédie of the Enlightenment, it actually needed 9 pages, big folio pages to fold out. You see all the different subjects there. And this is a modern representation of the scientific disciplines, which is kind of dizzying. And no, we are not labeling all the results, we're just labeling the branches, so to say. Not the leaves, not all the papers that are written, which is of course absolutely spectacular. And I think this is another thing, you know, knowledge is growing so fast that we are, I think, really are difficult orienting ourselves in this gigantic sea of information. And I think actually there is a certain tendency here to cut up knowledge in so many disciplines, sub-disciplines, etc., that I'm not convinced this is the most optimal structure of knowledge at this point. And I think one of the great things of being at the Institute is that we are sometimes have very little of these subdivisions. But the architecture of knowledge is changing too. It's really also becoming a global enterprise, so I'll say something about it. This is actually very strongly related to another fact, which is the way science is interfacing with society. And that's true, also changing. I showed the article of von Neumann in 1955, so we can now zoom back to the present day, and of course, the subject of climate change has changed terrifically. There are now regular, beautiful reports, the IPCC, the panel of climate change, brings out these reports actually this year, and started already in October 2013. There's a series of reports giving state-of-the-art of the knowledge there. Literally thousands of contributions. You know, each of these reports is more than 1,000 pages, at least the last edition, the 4th edition. And enormous amount of information, but in some sense the message that comes out is pretty simple. As somebody likes to summarize it, the 5 basic facts. It's real, it's us, it's bad. Most scientists agree, and there's hope. But you all know that the debate about climate change is not that simple. So, although we have this tremendous growth of knowledge, and thousands of papers and experts collaborating, you actually, if you look at public attitudes, you see something very different. And I think that has to do in the way science is interfacing with society. I think we are going through a time where, in some sense, the division, what is the scientific community, and what is the world out there, is changing. In some sense, all of us are becoming a little bit of a scientist. We're getting a kind of a more fragmented structure. Pieces of knowledge are all around us, and the interface between the scientific world and society is becoming much more complicated, to say it at least. Information is freely available. People talk about the University of Google. Fragmented knowledge, invalidated knowledge. And this is my favorite quote from a wonderful theoretical physicist. The problem with the global village are the global village idiots. And it's all around us. You know, I've had very distinguished colleagues of me come and say, well, you definitely have to read this paper about climate change. And then I said, well, who's the author? Well, Mr. So-and-so. Well, Who is he? I don't know. And then I Googled it indeed, and find the author is basically active in 3 fields: climate change, the so-called moon landings, and the so-called murder of John F. Kennedy. I think, wait a moment, if a very distinguished professor is coming with this paper, we have difficulty finding our bearing in this sea of information. Climate change, again, a terrific example, as you all know, is relatively small mistakes in one of these reports led to enormous outcomes in differences in public opinion. A few years ago, there was a mistake found, as you perhaps all you've got. If you Google IPCC, you immediately get images of the Himalayas, because there was a statement that the Himalayas would have been melted away in 2035. I think it was a misspelling, it should have been 2350. The number didn't percolate in any way to the conclusions of the report, but the effects on the public opinion were devastating, because people thought, well, if you don't even get your numbers right, can we trust you? And for instance, just to see, this is a recent poll among the American public and climate scientists, and you see that the consensus on the scientific side doesn't necessarily translate to a consensus on the general public side. So you can ask, how do we deal with this? How do we translate that into each other? And in fact, this is a story that has been done for a long time. In fact, it's interesting to see that in the debate between the public and the scientific experts, there have been many episodes which are very closely related, but just in different fields. Since most people have forgotten the tobacco wars. And there's this famous document in the tobacco wars where one of the PR firms for the tobacco companies has this wonderful saying, doubt is our product, since it's the best means of competing with the quote-unquote body of facts that exists in the minds of the general people. So one approach is, whenever you are uncomfortable with the result of an outcome of a research, you just ask for more research. Hyperscience, as it's called. So I think this is an interesting fact that, even particularly I think from the perspective of scientists, you move in this very different situation. And actually not only doing this here in the US or in the Netherlands or somewhere else, it's actually a global discussion. Last year, Nature magazine announced the 4th age of research, saying that there were previous periods where we had individuals doing research, then it was like collaborations, then it was research groups, and now it's actually international collaboration. And this is a wonderful graph that describes the collaboration between researchers across the world. It's a little bit similar to the things you see in the back of your in-flight magazine. But then this is actually scientific information flowing around the world. And it's interesting, you can look at the map, and I'm always very proud that the Netherlands is right here in the middle. And there are two things. It is wonderful that we are connected in this way. It's true, I think science, scholarship is truly one of the global efforts. But you actually see also, the globe clearly isn't lit uniformly. In fact, this is another illustration of that effect. This is an image of the world where countries are represented with their actual physical size, which is not the usual projection of the country. So you see, Greenland is much smaller than it usually is. It's over here. Africa is huge. And then this website, worldmapper.org, you can put any data and they generate maps. And this is a map of the scientific world. They only have it from 10 years ago. But you see, it's pretty amazing how whole continents disappeared. Africa has really become invisible, almost. Here is Singapore. Indonesia is almost gone. Of course, if you would go back to 2014, China and India would have grown significantly. But it tells you something about the global inequality also in terms of the scientific infrastructure. And this is more than just an issue of principle. It's also an issue of practice, because many of the global issues that the world is dealing with are also unevenly distributed. For instance, the global south is bearing much more the effects of climate change, of the loss of biodiversity, than we are in the north. And in fact, also this discussion about these scientific issues is uneven. This is from a recent poll where people checked whether people were aware of climate change. So you see it's almost 100% in terms of Western countries. But then, do you think this is a result of human activities? You see, it's a very different picture. And in fact, it's remarkable that a lot of research shows that, particularly in poor countries, people aren't aware of these things happening. Once they are aware, they are very worried, and they want to take action. So, actually, that could be in some sense an hopeful effect, because even political deadlock is not a universal effect. So perhaps if these different cultures come together, that might be some help. So finally, I want to say something about the nature of science, and perhaps because that's actually much more closer, I guess, or it's very close to my heart, which is, as I started, is about looking at the other side of the hill. So how do we do this? And I think here is, I would say, the aspects of creativity, of imagination, of wonder are guiding the typical scholar and scientist. And I want to give you an anecdote. This is actually a statue that was very close to my old secondary school I went to in Rotterdam in the Netherlands. And it's a statue of a chemist, Johannes van 't Hoff, who was famous because he got the first Nobel Prize in chemistry. So in that first year, 1901, the Dutch had 100% of the Nobel Prizes in chemistry. A little bit like the long track skating in the... And also I think it's a sign of the times, because these days, I think people don't build these kind of statues anymore for Nobel laureates. I think, it's in some sense, it was a period, I think, where science was very well respected. Actually, Van 't Hoff, if you ask what he did, he was the first person to realize that molecules are three-dimensional. In the sense of people always making pictures of molecules and making drawings, but he realized, no, a molecule is three-dimensional. So if I put it in front of a mirror, the mirror image of the molecule will be a different molecule. Now, you all know this now, because we know we have DNA and it's rotating, it's this circular structure, it's going one way, if it's going the other way, you can do this in the lab, it will be totally dysfunctional. In fact, there's a beautiful website, I didn't show it, which it's by a biologist who collects images of the wrong DNA, turning in the wrong direction, from famous articles. It's on the cover of biology textbooks. And usually I think it's a graphic designer who says, "Oh, this looks nice. It looks even nicer when I mirror it." Totally not aware of Van 't Hoff's contribution to science. But and I should say there's a kind of a very nice connotation also with the institute, because there is this asymmetry, the fact that the mirror image is not necessarily the same thing, holds even down to the very small particles. In fact, one of the heroic episodes of the early life of the Institute was the work of T.D. Lee and C.N. Yang, who were both in their early 30s. They were appointed as full professors at the Institute by Robert Oppenheimer, so it was a very, very brave appointment. And they asked the question, is nature mirror symmetric at the fundamental level? And this was like a question that everybody would say, yes, of course. A DNA molecule might be asymmetric, but the individual atoms are not. You just constructed it being left-handed, but there's no intrinsic favored handedness in nature. And then they said, well, let's just check. Let's go through all the experiments and see whether anybody checked whether there's a favorite direction. And they noticed that everybody was always in the mind that there's no difference between left and right. So nobody checked. So they wrote a paper basically saying, well, it could very well be asymmetric, and please do the experiments. The experiments were easy to do. They were done in Columbia by Madame Wu. And within within half a year, she found very nice proof that nature is not symmetric. And in fact, the weak nuclear force is totally kind of left-handed. And there's a famous saying by Pauli, Wolfgang Pauli, the physicist, that nature actually is a weak left-hander. The universe is a weak left-hander. And it's a famous, I mentioned here because it's an example where within 1 year from the paper, actually they got the Nobel Prize. So I told you about Higgs, who had to wait for 50 years. They were awarded the prize within 1 year. So you see somehow the spectrum of possible discoveries. But why I mention all of this? Because Van 't Hoff, when he did this work, was criticized. He was criticized, this is the end of the 19th century, and he was criticized by one of the most famous German chemists, Kolbe. And Van 't Hoff actually was, at that point, an adjunct professor at the veterinary school in Utrecht, in the Netherlands. And so Kolbe actually said, you know, well, he didn't do any real, precise analysis, etc. He just mounted his flying horse and went up to the mountain Olympus and just declared it to be true. And then Van 't Hoff was really upset. He was so upset that when he was appointed a professor, he didn't speak about his research. He spoke about the power of the imagination. Now, the interesting thing is that if you read the quote further down, Kolbe actually says, well, okay, he takes this kind of leap of faith, the power of imagination, when he goes on, if German science is not able to train people like this, we will lose the war on talent, essentially. So he's actually complimenting him in a very, very powerful way. But I guess Van 't Hoff was so upset when he read the first paragraph that he didn't care to read further. But then, so he has this inaugural lecture at the university about the power of imagination, and he does an experiment. So he treats the subject very scientifically. He makes a list of the 200 most famous scientists of the last, I think, 400 years. And then he put them in 3 categories. And the first category is scientists without imagination. He defines without imagination that no other interests, no, they don't read poetry, they don't interested in painting, so they do nothing else. And then there's the second category of scientists with imagination. And then there's a third category, which you call scientists with too much imagination. And it's quite a list, no? It's Leibniz and Newton and all there. And I think Newton is a very powerful example, because you all know he was this absolutely marvelous scientist. But at the same time, you know, he spent a lot of time after doing all this great work on optics and gravitation and the laws of mechanics on alchemy and trying to understand the books in the Bible and trying to basically understand how all of culture emerged. And so I think this actually is a wonderful story, because I think the point that Van 't Hoff is trying to make is that, you know, if you want to make a breakthrough, you have to reach far. Now, I never done karate, but somebody told me that if you do karate, you have to hit, and you want to kind of break through a brick, and people are doing this all the time, that you shouldn't point at the brick, but you should point behind the brick, because then you hit the brick with full force. And I think that's something that's definitely an effect, I think, in scientific research. We dream of things that aren't there, we try to measure them, we try to reach them, and sometimes we hit a brick wall, and sometimes we go through it. And I think that's the nature of science, and I think it's, to kind of finish, it's absolutely, for me, a total delight to be at an institution that I think totally embodies that feeling. You know, it's, I talked of many, many things that are changing in the world of research and science, but I feel actually the Institute of Advanced Study is one of these rare nature preserves, where we kind of keep some of that great quality. And I would often like to say that, you know, it's, we provide the most rarest of natural resources, you know, which is depleting faster than oil or gas or whatever, which is just free space and time to think. And I think we have seen, looking in the past, how powerful that freedom is, the freedom of imagination. And I think it will also be very powerful in the future. Thank you very much.
Next comes the standing ovation.
biggest problems facing the United States is the clash between science and religion.
Yes.
How can institutes such as yours and other institutes work with theologians to be able to bridge the gap and therefore find a methodology in which there can be common agreement so you don't end up sliding backwards?
Well, it's a wonderful question. I think it really, if you say it's a good question, often means you don't have an answer, I think. To say one thing, actually, the Institute, when it was founded, apart from its motto, truth and beauty, it had another credo, which was it's open for any people of any sex, race, and religion, which, by the way, was a very powerful statement in 1930, and turned out to be even more powerful when things were happening across the world. And in fact, the Institute was, in that sense, perhaps good to know, it's not answering the question, but has been transformative in many ways in opening up, I would say, the issue of diversity, both in the general academic sense, scientific culture, but also I think here just in Princeton, in the town. I think the Institute, I think we, as I said, we basically offer this freedom. I don't think actually I have a good answer how this particular question is answered and we can play a role. I think it's a tremendous element which it actually was totally missing in my talk here, which is, I think, key in addressing this issue of connecting science and society, because it's definitely a way in which people are expressing some of the same feelings that I talked about in my lecture.
All right, just to one step further, I think part of the problem is that lay people believe that scientists are not religious people.
Yes.
And that's a fallacy. And I think
it's true. Well, I'm also very proud that Freeman Dyson, who I think is one of our great treasures, has written a lot about this, and that's some comfort. I don't have any concrete answer. I don't think actually it's also part of my job in some sense to steer people, but I think I think at least the first approximation is we try to be open to everything and be undirected in the way the people think. Yes?
Based on what you see going on in terms of scientific advances, what is the area that people like us are going to be most surprised about in the next few years? I mean, we can't even imagine, I don't
Yes.
think, of what's coming and what it's going to look like and how surprising it's going to be. You've got different insights. You have any speculation?
Well, there's plenty of speculation. I think often the problem is it's not very imaginative. Right? It's a little bit like predicting yesterday's weather. In the sense that we see certain trends. So, as I said, the trends of rearranging matter at will, using the full power of quantum mechanics. So I think at some point in our life will for 100% be quantum mechanics. So we could have quantum computers, we could have infinite computing power, we could have infinite ways of rearranging our matter. How will it impact our lives? It's very difficult to say. I think actually, just to mention a few things where people are thinking about at the Institute, whether at some point even our science itself, like for instance our mathematics, could be completely, or could be a kind of a hybrid of humans and machines. We could have very bizarre effects of alien life. I think actually it's undoubtedly there's something like the Bilbo Yoga egg boxes that at some point will hit us. It's interesting to see what kind of a bad track record we have in predicting the future. And so the safest part, I think, is the development of technology. But it's much more interesting to see, for instance, perhaps we learn something about this missing 95%. And that might actually totally change.
Virtual science?
The way, just our position in the universe and what we are. And so plenty room of surprises, but I'm not giving any firm predictions here. In the back, yes. Well, well, I think actually, I would say that just in general, I think there's quite a consensus that, it would be really, really, really bizarre if we are the only intelligent people in the universe. And I think, what we definitely are seeing is that more and more of the habitats out there are very similar to the ones here on planet Earth. There is life started very early here. The universe is pretty old, so there's plenty of also opportunity in terms of time for this to happen. I think, and I think it probably are here with the majority of scientists to say, well, it would be very unlikely if we were alone.
Will we find them?
Or will they find us? Well, I think if you say in the next 10, 20 years, I think one thing we might probably get is firmer indication what some of these, what are the circumstances on planets close to other stars are. Perhaps, and I think that's put further away, we can see some indirect evidence of molecules which could be close to the molecules of life. To actually have visits of little green men, I think is a little bit further down the road. Yes.
When you put up that graph where it showed 97% of the world scientists believe climate change is occurring,
Yes.
who are the 3% and what do you believe?
Well, no, I think actually, certainly also, I think you learn, again, as a scientist, you should be kind of a natural skeptic. And so the question is, to which extent are you convinced? And I think actually I do understand some of these points. So of course there are great uncertainties there. For instance, people would argue, well, this is all based on computer models. All of these computer models are essentially the same, they're trained in the same way. So if there's some very systematic mistake we make in these models, that could actually make these conclusions invalid. For instance, I think there was a big deal made in some of the media about this kind of pause in warming of the last 15 years. I talked about this at the kitchen table, and my 7th grade daughter said, oh, I just learned that climate is the average on 30 years. I think, well, you're right. That's actually the one-line argument there. And so I think there's, and then I think there's sometimes also kind of a confusion of whether actually you are convinced by the arguments, or if you are also convinced that it should be getting the weight, the political weight that it has. Some people say, well, no, it's an important issue, but our other issues are more important, like dealing with poverty, or dealing with health issues, or, for instance, development is a much more powerful element that kind of puts ecosystems at risk than global warming. But actually, I think again, science is not done by consensus. And if you take all the major breakthroughs, probably they were all in the 3%, so to say, at that point. But here it is remarkable, certainly the difference between the two graphs. Yes.
How cold is it inside the collider? And how do we know that it's the coldest place in the universe?
Okay, that's a good point. So we know how cold the universe itself is, which is actually the temperature of this gas. To first answer that question, that the radiation of the Big Bang, so that's the light that kind of was born literally at 400,000 years after the Big Bang. Most of these light particles, these photons, had been kind of going through the universe undisturbed. So, but of course the universe expanded, and so that gas of radiation cooled down, and it's now down to a temperature which is 2.3 degrees above the absolute minimum. Now, to have these magnets, you have to make helium liquids, which, if I'm on top of my head, it's 1.3. So it's like half the temperature. But why is it the coolest place on Earth? Well, on the universe, because the whole universe is embedded in this gas of background radiation. It has at least that temperature, so the only way to go below that is make a refrigerator. So you need some kind of intelligent life to do this. And it's of course not quite right that that particular detector is the coldest part, because there are some parts in laboratories across the world where we reach much lower temperatures. But it's definitely cooler than the universe out there. Yes.
What advice would you give to middle schoolers or high schoolers who would come to you and say, what part of science should they devote their lives to?
Now, one wonderful thing of science is the enormous diversities of subjects. And so you meet many people working in many different fields. And there's this terrific feeling always that, you immediately recognize each other's enthusiasm. You say, well, this person is as enthusiastic about decoding the genome as I am understanding the Higgs particle. But you also know that you shouldn't change jobs. There's usually a very strong resonance with a particular topic. And that goes actually, I would say, like in 3 or 4 decimals, where you really know this is the field I want to work on. And you have to discover this. And so at some point I would say you know. And one of the great things I see with students that, for instance, in physics we have many students, which you think, which we like to say is the Einstein complex, they want to kind of write the equation that governs the universe. And then at some point it turns out either it's not interesting, or they are not really talented, or it's not fascinating, and then see the students move on to another field and blossom and really enjoy themselves. So I think there's no field which, by definition, is more interesting. I often feel science and scholarship is like you can't start digging anywhere. If you dig deep enough, you'll hit gold. And but it's very important that you start digging at a place where you have some intuition that this is the field I want to work in, and that can actually change. It can change in your career if people sometimes they totally change their interest. I would say that it's I think a correct statement that there's never been a period in the history of the Earth that there were so many opportunities, so many questions. So many new techniques, so many new phenomena that you can study. I think you're just, as I said, just the opportunities. Certainly because now we are starting to build our own subjects that we can study. It's really an infinitude. And the amazing thing, I pictured this graph, how do you find your way in this infinity? And the amazing thing is that there's still something like the natural curiosity of human beings, which are like a compass that go there. And one of the great experiences we more senior people have is that we have these young people coming in and they look at your field and they suddenly say, I want to go that direction. You say, well, that's totally the wrong direction. There's nothing there. We look there, there's nothing. Why would you? And they walk in and then they come back with treasures because they see something that nobody else saw. So my advice would be, if you're a young person, read about a lot of different things. Explore them, see whether you really are resonating to it, and particularly in the beginning, take the time to sample kind of many dishes. Yes.
Within the whole spectrum of science, is there some particular goal or accomplishment which you personally would love to see reached within your own lifetime?
I think so I'm a card-carrying reductionist. I really feel the universe is telling us that there is a system on which it's based. That's such a strong indicator. The fact that all of this, we reduce it to whatever, millions of molecules, then just 100 kind of atoms, then this handful of particles governed by a single equation. And okay, that's the 5%. This is really a trend. I think that nature is telling us there is a fundamental description of nature that I think Einstein had the hope, I'm not quite sure whether that will ever be realized, But once we realize what the answer is, we see that there is only one question that we could possibly ask. That the universe is kind of internally consistent. If you want it to be based in a particular way, there's only one way in which it can be fit together. That would be wonderful. I'm not sure that it will be that easy, but I think and many of my colleagues, often the question is, okay, suppose you go to sleep for 500 years and you wake up. What's the first question you would want to ask? I would like to see this equation of the... There's a famous mathematician, Hilbert. The greatest problem in mathematics is called the Riemann hypothesis. It's a conjecture of prime numbers. And he answered that question, if I wake up after 500 years, I want to know whether the Riemann conjecture was proven, yes or no.
One more question?
Yes, there, back.
The 95% of stuff that we do not know what it is, how do we know how much is energy versus how much is matter?
Oh, but okay, so that's a good question. So first of all, we need to understand a few things. So with E equals mc squared, any form of energy will have a mass, and mass will influence the gravitational effect. So the energy we measure in terms of the effect it has on gravity, which is the curvature, the expansion of the universe. Now, there are basically two effects. Now, matter has the effect that it's is an attractive force. So even in Einstein's theory, most forms of matter just attract each other. So they're kind of slowing down the expansion of the universe. The pure energy form, and that's something that Einstein discovered, that you could add to his equations a form of energy that's kind of in empty space. And that's the way you should think of it. It has a totally different effect. First of all, technically it's different, but more importantly, it can be pointing in the other direction. Actually, Einstein presumed this term because he was very worried when he found that we had this expanding universe, that the universe had a natural nature to expand. He felt actually you try to kind of contain that expansion and think of a force in empty space that would kind of control it and counterbalance it. And he invented this thing called the cosmological constant, or what we now call dark energy. In fact, it's exactly that term that was found, but the opposite sign. So it's actually a form of energy that's more like if you have a sponge, something you compress it, it wants to kind of expand even more. And so in a very simple way, you can see one effect is actually increasing the expansion rate, the other is slowing it down. And by going through very carefully go through the kind of time series of the expansion, you can kind of see the two different terms in Einstein's equation. So there's essentially two different terms in Einstein's equations. And it's an absolutely remarkable effect because it's a thing, I think, perhaps the biggest question that many of the fundamental physicists are thinking about is that what we have seen, and I'd like to say that the biggest thing to discover, to investigate, is actually nothing. Because it's the qualities of empty space. I mean, empty space, with Einstein, got all the properties of being able to curve and shape, so it becomes like a flexible material. But then through this effect, you see it's also filled with energy. And in fact, since the empty space has this natural power, it wants to kind of expand, it makes more of itself. So we get more. So the 75%, or I think it's now 68% of dark energy, that's just a snapshot of 2014. If you go 10 billion years later, or 100 billion years later, it will increase, increase, increase. So finally, that's actually quite remarkable that the whole matter part of the universe will be totally negligible component of our universe. So in the end, I think we would even understand 0% of it.
Thank you.